Good everyone, my name is Anthony Nathaniel, and today in our physics class, Global Education Zone, we'll be dealing with a topic known as refraction of light waves. So without wasting much time, let's delve into it. Now, refraction of light rays can be known as the bending of light when it passes the boundary between two media of different densities. So basically, if this is air, and this is the boundary between air and water. So refraction is basically the process whereby when light hit this air water boundary, this is the boundary. When it hits this boundary, it is bent. And note that when it travels from a region of less density to a region of greater density, it is bent towards the normal. So I mean, this, instead of going this way as it would in a straight line, it will be bent towards the normal. So it will bend downwards. Now that is a property of light waves and basically of majorly all waves. All waves undergo refraction. Light wave, sound wave, electromagnetic wave, whatever wave you can think of, they all get refracted at some point or another. And now refraction is characterized by angle of incidence and angle of emergence. Now the angle of incidence is the angle between the normal and the incidence ray. And then the angle of emergence is the angle between the normal and the emergent ray. Now, for when light travels from a less dense medium to a denser medium, the angle of emergence is always lesser than the angle of incidence. Now, let me explain the principle of dense and less denser. When you say something is dense, it means there's more of it packed into something. When you say something is dense, it's like something like a thick, something that is thick, that is jelly-like. But when you say something is watery, it is less dense, right? Something that is less dense, it is watery. It contains less molecules. So, just in the physical terms, when you see a liquid that is dense, it will be heavier and it will contain more matter packed in it given volume. But something that is less than will be more watery, will be lighter in weight. So that means air is lighter in weight than water, right? That means that's why it bends towards the normal when it passes through the boundary between air and water. Now, that means we are going to talk about Snell's law and the laws of refraction. Now, there are two laws of refraction. The first law of refraction states that the incident ray and the refracted ray at the point of incidence, they all lie on the same plane. So the incident ray and the refracted ray at the point of incidence all lie on the same plane. What that means is that this incident ray and the refracted ray, they all lie on the plane of incidence, and this is the plane of incidence. This horizontal plane is called the plane of incidence, and this vertical plane is called the normal. Now this incidence ray, it lies on this horizontal plane, this flat horizontal plane, and then this emergent ray also projects outward from the horizontal plane. So they are both on the same plane. Now the second law of refraction says that the ratio of the sine of the angle of incidence to the ratio of the sine of the angle of refraction is a constant and is known as Snell's law. Now that means the ratio of the sine of incidence, that's sine of I over sine of R, is a constant, and that is known as the refractive index of that medium. Now the refractive index of that medium is denoted by the particular direction in which light moves in that medium. Now if light moves from air to water, that means our refractive index will be the refractive index of from air to water. But if it moves from water to air, our refractive index will be the refractive index of water to air. That will be W rho A. So now what that means is that refractive index can have different meaning, depends on the direction of the light. So basically, let's move on. Moving on, let's talk about the experiments to determine the refractive index of a medium. Now imagine we have a glass cuboid, a solid glass cuboid, something like this, and then below that glass cube we'll put a pin, a colored pin. Now that this pin is below the glass, and then you set up an experiment with a retor stand with a search pin on that experiment. And now this search pin, you can use it to find out the point at which this pin below the glass cuboid, and that point where the search pin and that pin below the glass cuboid, that point where they appear to coincide, is called the point of no parallax. In a previous video, I talked about the fact that parallax is the apparent relative motion between two particles which are not the same distance from an observer. So stay tuned to the end of this video and we'll talk about the derivation of a famous law in refraction. So let's move on. So now when those coincide, we will notice that it's called an apparent distance, and the apparent distance is always less than the real distance. Now the apparent distance might appear to be something like here. That will be the apparent distance, whereas the real distance is from up to the down of the cube. So now that difference between the apparent ratio between the real and the apparent is called the refractive index. Now that means the refractive index, also known as n, or whatever you want to call it, of that medium is equals to the real depth over the apparent depth. Now that is one general formula for refractive index. Now and JAMB brings questions like this where they ask you to calculate the displacement, and the displacement is basically the real depth minus the apparent depth. Now moving on, we've talked about the fact that refractive index is a constant and it's known as Snell's law, right? Now moving on, let's talk about the explanations of different phenomena of refraction. Now I mentioned earlier that refraction is the bending of light rays when they pass the boundary between two medium, right? Now let me explain three phenomena which demonstrates and illustrates the process of refraction. The first one we'll talk about is the apparent depth of objects, and this is what we'll talk about here. So how that works, I will set up a diagram. Imagine you have a bucket of water, and then inside that bucket you have a pin at the bottom of the water. Now, and that water is filled to a particular depth. Now, as an observer, light from the ball below the surface of the water reaches your eye, and when it gets to the medium, the boundary between the air and the water, it becomes refracted. So, and I said earlier that when light moves from a less dense to a denser, it moves towards the normal. But when it moves from a denser to a less dense medium, it moves away from the normal. So that means this rays will actually be deflected outwards. So now when you trace it backward, you will notice that they meet at a point which is at a very much higher distance than the depth of the ball. So now that point is called the apparent depth, and that point, from the distance between that point and the top of the surface, is called the apparent depth, while the distance between the real location of the ball and the top of the surface is the real depth. Now, but your eye is deceived and it sees that ball from the apparent depth because of the effect of refraction. So that is why most of the time when you put a pin, or when you put something in water, it looks as if it's closer to the surface than it actually is. And even in a swimming pool, when you get to the swimming pool, the depth of the swimming pool always looks closer to the surface, but when you enter the swimming pool, it's actually much deeper than what you thought. So now let's talk about another illustration of refraction, which is apparent bending of objects when they enter water. Now on this, you can explain this as, imagine we have another bucket of water here, and then we have it filled to a level of particular level of water, and then we have a stick immersed in the water. Now light again reaches your eye from this part of the water, and imagine we have two light rays here. When these light rays come to the surface, they also bend outwards, and when they coincide, they meet at a particular point, and that is where the apparent bending happens. So the stick appears to bend. So, and when you trace the straight line through to meet the real part of the stick, it looks something like this. So it looks bent. So whenever you put an object in water, because of the phenomenon of refraction, the part inside the water appears to be closer to you, or it appears bent towards your direction, and that's because of the fact of refraction. Now, lastly, we talk about the bringing of objects into view, and next we'll talk about again a bucket of water. Imagine you have a bucket of water, and then you have a pin or a tiny object inside water, and that object is opaque. Imagine you have such an object, and then your eye is at a corner of the bucket of water. Now this is the bucket of water. Your eye is at the corner of the bucket of water, and now you cannot see this object when this is empty. So when this container is empty, the light cannot bend into your eye. But when it is filled, or when it is filled to a particular level of water, you notice that when light rays that pass from the water to meet your eyes, when they pass, they are actually bent away from normal. They bend away from normal, and when they combine, they form the image they bring the depth of the image to a much higher surface, and you can now see the image. You can now see the image of the object, though it is virtual. You can now see it at a much higher object, and so that is how that object becomes visible. So, and next we'll talk about the phenomenon of total internal reflection. And total internal reflection is a very, very important phenomenon in our world today, because it's applied in our communication systems, and even in every network systems that make use of what they call optical fiber or fiber optics. Now, this fiber optics is an application of total internal reflection, and I'll talk about it in detail now. Now, total internal reflection is a process whereby when light moves from a denser to a less dense medium. Imagine this is our denser medium here. When light moves from this denser medium to a less dense medium, like this is a glass, and this when light moves to the air, then there's a particular angle of reflection, the angle of refraction at which the angle of incidence in the denser medium. So that particular angle of incidence in the denser medium, where the angle of refraction at the less dense medium is 90, is called the critical angle. And above that critical angle, the light is totally reflected. That means once the angle of incidence here is beyond a particular angle, this angle of incidence, when it gets to the barrier at a particular angle, it hits here. Then when you increase this angle and when you get to a particular angle, it actually goes at a 90 degree. So it is 90 degrees to the normal, and that process is known as total internal reflection. And to be defined, I will define it as the process whereby light is bent 90 degrees at a lesser dense medium when the angle in the incidence medium is greater than the critical angle. And that critical angle is characteristic of every particular medium. Every particular medium has its own inherent critical angle. Now, total internal reflection formally is the reflection of light is the reflection of an incidence ray of light at the interface between the medium of medium of incidence and another medium of lesser density, provided that the light is moving from a medium of denser to less dense, and also that the critical angle in the denser medium is exceeded. So there are three applications of total internal reflection. We have mirage, fish eye view, and I want to explain fish eye view because it is similar to mirage, but I will explain mirage. Now, basically, when you are moving on a sunny day and then the sun has been hitting the earth for a long time, when the sun hits the earth for a long time, the molecules of air close to the earth surface become very hot, because air is matter, and when the sun hits matter, the matter absorbs some of the energy of the sun and becomes hot. Now, you know that temperature is also proportional to the kinetic energy of the particle. So that means those molecules acquire more kinetic energy, and from our gas laws, we know that the temperature of the particle is directly proportional to the volume. So that means those gases expand because their volume increases with temperature. Volume is directly proportional to temperature. When they expand, they become less dense, because as I stated earlier, when something expands, it occupies more space and it's less dense. There are less of its parts. So that means that less dense air always wants to flow to the top. Because you know that when you have something less heavy, something heavy will flow to the down, while something less heavy will flow to the top, right? So that hot air will flow to the top, and in that process, that hot air, there's still some amount of that hot air trapped. So, but when light from the sun hits a particular object and it's coming towards the earth, it passes through these layers. So it passes through the denser cold air, and that denser cold air is at the top, and when it gets to the lower area of hot air, so that's before the hot air escapes. So that's before the hot air escapes towards the closer to the atmosphere. Now, when it gets to the hot air, it travels from a medium of high density to a medium of low density. So that means basically it has become total internal reflected. And once, as a result of that, the direction of the light reverses, and when it meets your eye, it appears that the light is coming from the ground. So in the diagram, I will illustrate this as, imagine you have the sun here, and then you have a tree. Now the sun rays cast on that tree, and then when it gets closer to the earth, they create a portion of less dense air. Now, and when it gets to this less dense air, that light is totally reflected. That's what they call total internal reflection. And when it bends at an angle of 90 degrees, and then when it bends and it gets to meet your eye, the light appears to be coming from the ground. So that means you are actually seeing a reflection of the sky and reflection of the tree. So it actually looks like a pool of water. So but it's actually a reflection of the sky caused by total internal reflection. So now, having covered most of the theoretical background of reflection and a few of other calculations and whatever, so now let's move on to let me make a derivation for a very important equation using reflection. So now, as we know it, total internal reflection is not just applied in sun and the moon and whatever. So now, but it's also applied in real objects. Now, and I will give an example. This is a glass prism, and this is an equilateral glass prism. I will use it to explain a lot of things in this video. Now, the first thing I will explain will be the fact that this equilateral triangle has 60 degrees each at each of its vertices. Now, we are exploring a phenomenon where the light hits the one side of this, and now this is the normal, because you know that you always have a surface, and you always have a normal to the surface where it forms the incidence angle. Now, this normal, when it hits normal, it becomes refracted, it's bent in the medium, and then it's when it hits normal again at the other end, and then it's bent outwards. Now, the angle between the normal and the angle and the incidence ray is called the angle of incidence, and the angle between the normal at the other side and the emergence ray is called the angle of emergence, E. Now, there's a particular path which this light is supposed to pass, but which it doesn't pass, and that is because